Welcome everybody on Zoom, welcome everybody in the lecture hall. Today, we should be able to finish what we started on graph databases. In particular, I told you that there are two main paradigms in graph databases. One that we covered yesterday that is known as the labeled property graph with Neo4j as an example. The second paragraph is called triple store or RDF. This is the other technology that's also known as the semantic web. It actually used to be called Web 3.0, but now somehow Web 3 means something else. But a long time ago, this is what it was for, semantic web. All right, so what do we need? Something different. Well, we saw that for the label property graph, it's very powerful. You can use pattern matching like this. Now, this is what SQL cannot do. We saw that the way that clauses work is actually quite similar to what we saw with JSONic, in the sense that we have a sequence of clauses, you know, that just one after the other. And these clauses are chained in the sense that they propagate streams of tuples, right? So in JSONic, the streams of tuples were based on the variable, you know, starting with dollars. Here, it's more based on the names of the fields and the name of the variables without dollars that you give, right? But basically, the principle is exactly the same. Every clause takes as input a tuple stream and outputs a tuple stream to the next clause, right? All the way to the return clause. And then the return clause outputs something. Now, it might be a bit counterintuitive that what is output just looks like a table and in fact is displayed as a table on the screen, right? So it shows how tables are natural. But we saw that since the types of what you can have in the table includes also nodes and relationships and paths, then the table really is just a structure in that case to return results. All right, so this is what we saw. But there is criticism on labeled property graphs, and the sort of things that you frequently hear is that labeled property graphs either are too complex, you know, or they are too verbose in the way that they that they expand the graph. They are unnecessarily complicating the model. Another piece of criticism that I gave you last week that you hear is also that in the case that your data is actually structured and that you do have the same properties for all nodes in the same label and that every node is exactly in one label and so on and so on and so on, then actually you should be using a relational database, right? You shouldn't be using a graph database. So a graph database in the sense of the label property graph is really when you actually have graph algorithms. We try to traverse the graph, you're trying to solve for some graph algorithm problems. This is what it's really for. So you really have to think critically about these things and ask yourself, is it the best thing that I can use? RDF has a different approach. It's much simpler actually than labeled property graphs. Because in RDF, there you go, we have only three, no, actually, let me put it simpler. We have only one thing that exists. There's only one first-class citizen in RDF that's called a triple. What is a triple? It's something that is made of a subject, a property, and an object, right? It basically would correspond to an edge in the graph. But in order to have an edge, you need a source and a target, right? So every triple is made of three things, as triple indicates: a subject, a property, and an object. In that case, we say ETH Zurich is located in Switzerland, ETH Zurich in the subject, is located in is the property, and Switzerland is the object. So first, you notice that we can express real life things, right? But this is not so surprising because the notion of graph has to do with the concept of knowledge base. But basically, a triple store is just millions or billions of these triples. That's it, period. I'm actually done with the data model of triple store, kind of. That's what it is about. I just need maybe to give you a bit more indications on what the subject, how the subject is modeled, how the property is modeled, and how the object is modeled, right? Because this is just a picture right here. But in practice, what is it, right? Just like we saw in the case of the label property graph, that we have strings to identify labels and properties, that we have a type system and so on. All right. So everything, you know, it's if you correctly remember, that's the W3C, right? The W3C is the same institution that standardizes the web and HTML and HTTP and so on. It also standardizes XML, XML schema, xquery, which is the XML pendant of JSONic. So that's the reason why you already saw these HTTP-like namespaces, right? In XML, we use HTTP URLs for namespaces. This is because this is how at W3C people love to name resources with URIs. So it shouldn't be a surprise to you then that the subject, the property, and the object are commonly URIs as well, right? Stuff that starts with HTTP. But again, it's not a URL in the sense that you wouldn't put that in the address of your browser, right? This is really just a resource identifier. So we have here the first URI could be seen as some identifier for ETH. And the second one, I used an example.com domain. By the way, this is what it's for, example.com. It's actually reserved for using for examples in teaching. So example.com/countries # Switzerland would be a URI for Switzerland, right? And basically, what you store as the triple would actually be the URI of the subject, the URI of the object. The property also is a URI. So a triple is just 3 URIs. Right, in general. We see it can also be literals, but for now, think of it as a URI for the subject, a URI for the property, a URI for the object, and the URI is just a resource identifier because the subject is a resource, the property is a resource, and the object is a resource. Okay, who is following? Okay, all right. But you might have noticed something, and I'll come back to it later. All the URIs that we use in RDF, they have this sharp thing. You know what sharp is, right? It's a fragment. When you use it in your browser, it actually directly jumps to the part of the page that has this fragment name, right? So everything in the URIs in RDF has this sharp with a fragment somewhere, and I'll come back to it because there's a few things to clarify there. Okay, so generally you can make triples out of 3 URIs, and you can also use literals. For example, if you want to say that there are, what's the latest number, 23,000 students at ETH, then you don't need a URI for 23,000, right? You can just use directly a number or an integer or a string, or, you know. So this is why instead of a URI for atomic values, you can just go ahead and use literals, right? This is nothing new. It's the same we saw in the JSON, XML, and everywhere else, right? And the good news here is, again, because it's W3C, all of the XML schema types are here. The same types as in JSONic, as in JSON. It's always the same list of types. And again, here, these are exactly the same types: dates, binary, date, time, shorts, bytes, integer, and so on, decimal. Okay. I also want, just in case, to clarify, because I also wrote IRI here. This is something I already mentioned. Normally, we should be calling these things IRI. In fact, we should be calling everything IRI, even what you type in the address of your browser. The problem is that it didn't catch up, and nobody actually says the IRI. Everybody continues to say URI. So this is why I also tend to continue to say URI, because that's the common practice. But at least in theory, you should know that normally it's supposed to be called IRI. Okay, so a third thing that you could see in RDF is a so-called blank nodes. And in fact, this was a question that was also asked yesterday for the label property graph, like, does a name have to have a label, or does it have to have properties? What does it mean when it doesn't? Well, you can have a blank node in the sense that it's whatever it is, but it's defined through the relationships that it has with the other nodes in the RDF graph, right? So for example, the ground on which we are here, ETH, could be a blank node, and then we can see ETH is built on whatever ground that is, right? We don't give it a name, and that ground that we are on is a subset of Switzerland, right? So that's called a blank node, all right? So you can have URIs that are resource identifiers. That's most of the time, that's what you're going to have. You can have literals, if you have a number or a string or a date or whatever, and you can have blank nodes that don't have anything, that are just whatever they are. And then all I need to tell you then is what goes where, right? For the subject, for the property, for the objects, can we have URIs? Can we have literals? And can we have blank nodes? So let's start with the object, because that's the easiest. The object can be anything. It can be a URI, it can be a literal, it can be a blank node, right? The property always must be a URI. always. It wouldn't make sense to use a number instead of a verb, right? I can say like ETH 23,000 Zurich, it doesn't mean anything, right? So this is why, and the blank note, that's the same. It would be like a phrase without a verb. So the property must be a URI, and the subject can be a URI or a blank note, right? It can be a URI or a blank note. Why not a literal? Because you could imagine making statements like 23,000 is not a prime number or that kind of things, and then the subject is a number, right? But this is not allowed, at least in the basic in the basic version of RDF, right? For whom is that clear? What is allowed? Okay, so this is the yes/no table. But it turns out that there are people who are probably brilliant and who have ideas of generalizing things that in a subsequent version, they say, you know what, let's just relax things and just allow anything anywhere, whatever that means. And then people can just go ahead and build triples in that way. But I don't recommend it. I mean, this is really, it's very likely that this is where you want to be in. If you do that, then you need to know what you're doing exactly. All right. Okay, so this is the data model. And again, it is so simple that it's easy to summarize. We just have billions of triples. A triple is made of a subject, a property, and an object. And the subject, the property, and the object, they can be URIs, there can be literals, or they can be blank. And we have a table that tells what goes where. Okay, that's the data model. But of course now, as we did in almost every shape that we've seen so far, we have syntax. Tables can be represented in CSV, trees can be represented in XML, in JSON, in YAML, even in Parquet, in the binary form and so on. But let's focus on text now. Is there a syntax for RDF? The answer is yes. In fact, there's plenty of syntaxes for RDF, just like for trees. I'm going to start with the easy ones because that's probably the more visual, and I don't want to scare you right away with the XML version of the syntax. But I'm just putting a few of them here, right? Let's start with the easy one. It's called turtle. Okay, so here's what's going on. We have here two triples. ETH is located in Switzerland, and ETH has a population of 25,000, right? So these are two triples. You see, there's a subject in blue. There's an object in orange, lighter. And there is a property in lighter orange, and there is an object in darker brown, right? So subject, property, object. Now I have to say a few words about these Q names, because you might recognize the Q names here with the colon and the prefix and so on. And you might think, okay, but I just told you these are URIs, and now we see Q names. Well, in fact, the way that Q names work in RDF is not the same as in the rest of XML. In fact, it's much simpler because what they do is they just concatenate stuff. So for example, this, let's take the country Switzerland. What they say is that they take this namespace here and they paste the local name after the namespace. So when I say country Switzerland, and countries is bound to this URI right here, to this namespace, what is actually happening is that this is building this URI right there, right? This is what's going on, okay? So do not be confused by this very strange use of Q names in RDF. This is how they do it. They just paste the namespace to the local name, and there you go. And this is why you still get a URI, just a longer one. Okay, so now you see, given these bindings here, this is just a fancy way of binding a prefix to a namespace, prefix to a namespace, prefix to a namespace, and then we have a URI, a URI, a URI, a URI, a URI, and a literal. And this is the period, the dot here, that basically just says that's the end of the triple. And you can have millions and billions of triples like that. But of course, we are lazy, and you probably notice that ETH self is repeating twice. Right. So how do we avoid repetition? Well, these very smart people who designed the syntax figured out that you can use a semicolon here, and then that basically repeats the subject. So then you just say, okay, ETH is located in Switzerland and has a population of 25,000. And if you're also lazy to repeat a property, for example, you want to say that it's located in Switzerland and in Europe, just use a comma. Right. So whenever you have a comma, it means you reuse the subject and the property. And whenever you have a semicolon, you reuse the subject. And then you go ahead with just the property and the object. For whom is that clear? Okay. There is another syntax called JSON-LD. This syntax also has, you see these bindings from the prefixes to the namespaces. It has the same ID that you paste the local name here to the namespace of the prefix. And here we have the subject factored out in this @id field. Then we have property object, property object, property object. And you see here, these are URIs. And again, here it's just a literal in there in the JSON syntax. So you see, this is the same thing. This is one syntax. This is turtle, and this is JSON-LD. All right. Okay. So now we have the XML syntax. I hope it works with the colors. I mean, I used to do it using green and red and so on, but I know that not everybody can distinguish, so I try to change the colors. I'm not sure. Can you distinguish the three? Okay. So I try to do the same here in XML because it can get complex. So what we have in XML is the same idea as in JSON, that the subject is factored out, and then you have a list of properties associated with objects. So we have here this RDF. It's just like in XML schema, it's called XS schema and so on. When in RDF, it just starts with RDF. Here, that shouldn't surprise you. That is the RDF namespace. But here, of course, this is XML, right? Here, this is in the sense of XML as you are used to. And geo here is the namespace for that we use for the properties right there. So then we say RDF description about ETH. So we factor out everything that is with one subject in a description element right there. And then we list the properties. So we have three triples here that all share this common subject. ETH is located in Switzerland, ETH is located in Europe, and ETH has a population of 25,000. Okay, for whom is that clear? All right, and you see here that there is a small difference, is that here we use this short syntax with the prefix and the local name in JSON. In XML, we use the full URI, and you see how it's pasted here. That would have been the namespace, and we paste the local name. But in this resource that contains the object, it's the full URI, not using the abbreviated syntax. Okay, so now we have three tuples. And again, just so that it's absolutely clear, the semantics of RDF for this geo is located in, interpreted as RDF. So this is outside of XML. This is actually interpreted as pasting the namespace and the local name. Well, I hear all the XML people screaming with that use of QName, but this is, this is how different communities think differently. All right. Okay, is it all clear for the syntax? So you see, it's just in the end always the same. You have a flat list of plenty of triples, subject, property, object, and you have plenty of syntaxes that can express them, turtle, JSON, XML, and many, many, many others. But you really need to understand it, if that wasn't clear, that the syntax is only syntax. What actually matters is when you parse the syntax and then have a representation in memory of this list of triples. And then you don't care if it was JSON, turtle, or XML, it doesn't matter. Okay? Okay, now we need to query, and I can tell you a few words as well about the query language for RDF. It's called Sparkle. Sparkle, to not confuse with Spark SQL. Sparkle is written S-P-A-R-Q-L, and that's how you query RDF. So we saw Cypher yesterday, and now that's a second language, but I'm not going to go that much in the details of that one. It's just to give you a feeling, right? So you see again, Cypher works on a label property graph. Sparkle works on a triple store. So this is what Sparkle looks like. Surprise, surprise, it looks just like SQL because it has these uppercase keywords there, select and where. So you can define in the language with keywords, of course, uppercase so that it looks like SQL. So prefix, geo, and then this, and countries, and then this. So you can declare whatever prefixes you want to use. And then we say we select S, where S is located in Switzerland. So you see here, this is basically a pattern. We are looking for this triple, But this question mark here is how you have variables. So instead of using dollars like you would do in languages like JSONic or others, here we use question marks for the variables. So the variable S, question mark S. So we look for something, whatever that is located in Switzerland, and we select that whatever that is, right? So this looks in the triple store for a triple where S is located in Switzerland, okay? We can also have multiple constraints in the where clause. So we could look for something that is both located in Switzerland and delivers a bachelor's diploma. We can also look for something that is located in whatever, and that whatever is in the continent of America, right? That's another example. So you see, you can have multiple variables here that you reuse, right? And you can also have similar syntactic constructs like the limit clause here that only returns 10 of the results, and so on and so on, right? Okay, you can order by as well. It's always a better idea because, as I told you, if you just use limit and offset without order by, it's a bit non-deterministic. But if you order and then limits, then you're guaranteed to get the first 10 in that case, right? So here we look for S and name such that S is located in Switzerland, S delivers the bachelor's diploma, and S has the name, right? So that basically fetches the name of S. And then we order by name. So by default, that's going to be ascending alphabetically and get the top 10, okay? So this is what I wanted to show you. I'm not getting into details because, you know, this is a lot of query languages to digest. I'm aware that it's tough to learn languages, but the only thing that I want you to understand is on the very high level, the look and feel of Sparkle, right? This is all I want you to understand here. And also for the exam, we are testing a restricted set of languages, not all of them. You need to master SQL in PostgreSQL, that's in any case. You need to be able to write queries in PySpark, right, using Python and using Spark RDDs. You need to be able to use Spark SQL, which is just the dialect of SQL used in Spark. That is also something you need to use at the exam to write code in. Of course, if you prefer to use data frame transformations rather than Spark SQL, nobody will prevent you, right? You can also do that if you prefer. But Spark SQL, I think for many is easier. And finally, JSONic. These are the only 4 practical things that you'll have at the exam where you need to code. It's PostgreSQL, SQL, PySpark, Spark SQL, and JSONic. You won't have to write as a practical exercise, I mean, the Cypher or Sparkle or whatever, right? This is just theory. You might have questions in theory, but you won't have to code in that. Okay. Everybody's following? Okay. So I hope it reassures you that you don't think like, oh my, I'm going to have to learn Sparkle. No, don't worry. That's not what I'm saying. Okay. So now let's go into the use of triple stores because it is actually quite popular. I'm going to surprise you in artificial intelligence because yes, there is not just machine learning in artificial intelligence, there are other things. And in fact, this is before machine learning was even popular because back then there were other kinds of systems that were trying to do artificial intelligence like expert systems and so on and so on. And one way to try to derive artificial intelligence is to have a knowledge base, and that knowledge base can be a triple store, which is just a set of millions of knowledge items. But of course, if you do that, you want to put some constraints in the way that you actually do it. Because if you just let people go ahead and write whatever triples they want, especially using the extended semantics, like you can have anything anywhere, and you just like that doesn't really mean much, right? So you want to actually have a bit of structure in the way that you structure the knowledge. For example, you would like the property to kind of be a verb or has a semantic meaning of a property, and so on and so on. Okay, for this reason, there was an extension of RDF called RDF schema. That shouldn't be surprising because whenever you want to add structure somewhere, you add a schema, right? This is how you do it in JSON with JSON schema and JSON, XML schema. The same goes in MongoDB. You can add a schema to a collection if you want to constrain it. The same goes in Neo4j that I told you can have a schema to constrain the properties and the relationships. Well, the same goes for RDF. You can also define schemas in RDF. But the way that this works is actually very taxonomy oriented, in the sense that you really think to put your knowledge base hat on, right? You want to classify things. You want to express truths about the world. So you need to classify stuff, and for that you can use classes. For example, a class could be universities. A class could be countries. A class could be furniture pieces, right? Chairs, tables, and so on. So you can have classes, and a class is just a set of resources that belong to that class, right? It's like set theory. And then a property, you can also define the set of all properties, right? The property can be is located in, has a population of, and so on and so on. So you can have plenty of properties. And what happens then if you have classes, it acts a bit like a type, like ETH has the type university if you want. So what you can go ahead, or the type school, there is a shortcut in the syntax that is introduced with schemas, is that you can have a property type that tells you the class in which a subject is. So I added here a fourth triple that basically says ETH is of type school. In terms of what I told you, it means it's in the class called school, right? But a class is itself a resource. It has a name, right? So the class also has a name called school. So ETH is of type school. And in fact, you can shortcut that by removing that fourth triple and just replacing, because otherwise it's always RDF description, you can replace the element name here with the name of the class. So basically it's easy as a human to read, right? We have a school called ETH that is located in Switzerland, that is located in Europe, and that has a population in 25,000, right? So you have this hidden fourth triple in there that says ETH is a school, right? But this is a special triple because it's information on the class to which ETH belongs, right? So ETH has the class school. Okay, so this is the triple basically right here. But again, you notice that this property right there is in a special namespace, RDF. So this is why this property is very, very, very special. Okay, and so once you have started to classify things and to organize your knowledge base about the world, then you can start doing logical inference. You can write programs that are going to try to infer things, like syllogism is an example. You know, it's a classical one. All men are mortal. Socrates is a man, therefore Socrates is mortal, and so on. So you can basically start inferring things. But of course, for this, again, I repeat, RDF is not enough. You need an additional layer of semantics on top of that, right? And this is what was known as Web 3.0 back then. So there are plenty of meta classes that are predefined in the RDF schema namespace. So you have the class resource that basically contains everything, because everything is a resource. Then you have the class. So it's a class that contains the classes, right? So university would have the type class. You have the class property that contains all properties. You also have a class that contains the literals, a class that contains the data types, right? It's really metadata. A class that contains all the HTML values, a class that contains all the XML literals, and so on. And again, here I know this, I mean, personally, it starts giving me headaches because of the level of thinking that you need to have in order to think about these things, right? But this is very powerful. You can then have self-awareness because the whole system can reason about itself. And for example, you can have any resource can have a type, any resource can have a label, and any resource can have a comment, right? So these are properties. There are properties on properties, because a property can have a range and a domain, just like a function, right? So, and a property can be a sub-property of another property, right? It means if A is a sub-property of B, that whenever A is true on a subject and object, then B is true as well, right? So A is a sub-property. And then you also have the property of subclass of. For example, university is a class that is a subclass of institution, for example, right? So that's the sort of things you can do. And all these things in the center of your screen, these are properties. These are all properties, but these properties can be properties on classes and so on. For example, class is a subclass of resource, right? So the set of all classes is a subset of the set of all resources. That's because a class is a resource. A range, the type has the range class, right? The range, that's what can be on the right of the type property. So Here, you notice that's why it's giving me the headaches. Type is on the left, so it's a subject. It's a statement about the property RDF type that has the range class. What that means is that whenever you have a triple with type in the middle, whatever is on the right must be a class. This is what it means. So this is the actual data that ETH has the type school, and this is meta. This is meta because you're making a statement about the statements you can make in RDF, right? So type E has the range class. Subclass of has the type property, right? This is again self-awareness and reasoning on oneself. So you see, when you build a system like that with plenty of resources and classes and properties and so on, and build a gigantic triple store, this is also called an ontology, and the people doing that are called ontologists. Right, they are dealing with this kind of knowledge graphs and knowledge bases. So it's a whole field all by itself with plenty of people working on that to try to model the real world semantically. They try to do it on a standalone system, right? Just store all of the information. Sorry, what I want to say here is there is a name for a much more powerful system than RDF and RDF schema that's called DALL-E. It's basically just taking the whole thing to the next level. But I'm not going to scare you with that. I'm just staying general here, right? So you see, we have XML that we saw as a syntax for trees, which acts as one of the possible syntaxes for RDF, that is a model for triples, and RDF itself acts as an implementation of all, that is this ontological framework on which you can reason on knowledge. Do we have a question on Zoom?
You somewhat already answered it, but somebody asked, what is the difference between ontology and this type of store?
Oh, so ontology is a very general thing. So this is an implementation of an ontological framework, right? You can probably do ontologies in many other ways. Ontology, I think the meaning of the word ontology is whatever exists in the universe, whatever is in the universe, right? Ontological, as opposed to epistemic. Epistemic would mean what you know about the universe, right? So an ontologist is somebody who reasons about the universe, or whatever knowledge base you're reasoning on, right? So RDF is just one implementation and one way of doing that, right? So what I hope I showed you, of course, we didn't go in detail because my only goal here is to give you the high-level idea. Hopefully now you see that there's not only machine learning in artificial intelligence, and there's other ways of reasoning on things. Okay. And some people actually, I saw in real life what some people are doing. They take data that is in a database, for example, in a data lake, or stored as XML, stored on JSON. And what they do is they try to take that data and convert it to triples. They convert it to RDF, and then they try to reason in that way, right? So this is what they are doing. I would almost call it they shred it to RDF, because, well, that's really like to the atomic level when you reduce the data to just triples. Okay. So this concludes the graph databases. So I just want to show you there's plenty of technologies around that. PGX, there will be a guest lecture next week. They will explain to you how they solve the sharding. So PGX is Oracle's graph database. GraphX is a library that runs graph queries on top of Spark. So you see it all works together. So if you're interested, you can take a look as well. And then there are other technologies like Turi, Apache, Giraffe, and so on and so on. But basically, it's all the same idea of organizing data in graphs. Okay. Any questions? Okay, let me see the time. 48. So I can maybe start another part and, well, not a new part, but tell you a few things about performance. Okay. So again, this whole thing about graph databases and RDF and so on, you could do a whole university course about that. People could spend 14 weeks explaining to you everything that there is. This is only 1 week's worth of material. So my only goal here is first to give you an intuition of that. But second, my main goal is that you see that graphs are a shape like any other. Just like the other shapes, there's a data model, there are syntaxes, there are query languages, and so on and so on and so on. Right. Okay. So then let me talk about something else, and we'll do cubes next week. All right, so I'll see you on the other side of the recording.